But with the induction loop, you are not directly measuring the field components of the Earth. You are only measuring the shift in resonant frequency. That's what you're doing here.
One question. Wouldn't you not also get a negative voltage when the vehicle leaves the area of the loop?
This voltage is proportional to the shift in resonant frequency. Yeah?
Oh, okay.
There is no change in output voltage here. The voltage will vary, but only due to the shift of the resonant frequency of the tank circuit. Yeah? So there are no negative numbers on this output here. Because what is going on? You have this resonance curve of the circuit. Normally you excite the circuit with the tuning frequency, and if the resonance circuit is changing due to the changes of your inductive component, then this resonance curve will be shifted. It won't change the way it looks like, but it will shift when other resonance frequency, F2, from F1 to F2. So the curve will be shifted, and what you are measuring is the difference between that voltage and now we are here. So the voltage will go down, and after the car leaves, the voltage will be restored to the prior value. That's what's going on. You shift the curve of the resonance circuit. No? So you're back to recording mode. So any other questions? Okay. Then we will continue with
sensors.
So actually today we will not continue with sensors. We had a lot of sensors yesterday. We will continue with a little bit of theory, because first thing we need is to have a system of units. So the question is, what are we measuring here and how we do the measurement? So the question is, what kind of framework do we have to do some measurements? So, and today we will derive the basics for such a measurement, such a framework. You all know this. This is the SI system. But before focusing onto the SI system, we will develop some ideas. What do we need to do any measurement? So if you are doing a measurement, normally you're grabbing a measurement instrument and you're reading the numbers. But there is a lot of stuff inside the measurement and a lot of progress until we can produce such a measurement. But on the other hand, let's focus on a very simple problem. You are at the position P1, your colleague is at the position P2, and you would like to tell a third person, maybe P3, how far is it from P1 to P2. So that's the basic ideas of this framework. And on a historic scale, what has been done? So first of all, we have to define what is this. From P1 to P2 is a distance. So it's a length. And in the second instance, we have to, how do we describe this length. So we have to have some, we call it a unit, a basic unit, and then we can see how often this unit will fit into this distance. And this was the first way how human defined some physical quality. The physical quality is distance or length, and the unit, it was not always, today what is the unit of distance?
Meter.
The meter, but it, on a historic scale, the meter evolved very lately, so around 1800 with the French Revolution. But before, and there are some countries, they still have this unit, this was the unit of the feet.
Mm-hmm.
So that's quite a natural way. You walk along the path and you're just counting your steps or feet. So feet and steps not exactly the same, but the step width is, you can say the step width is nearly 1 meter of an average human. Huh? But the definition of the meter, it's rather curious. Yeah? And all to these units, so there is nothing in physics that gives us the size of a unit. So 1 meter is a completely arbitrary number. So there is no physical clue to define 1 meter. And that's the problem if you setting up this framework. There is no clue or binding within physics that gives you the length of 1 meter or 1 kilogram or 1 second. So these are completely arbitrary numbers. It's a historic evolution. So, and this gives us further idea how do we do a measurement. If we're doing a measurement, first of all, we have to define the physical quality. Let's say the physical quality is X. It might be temperature, it might be distance or length or whatever. So first of all, this is the one fundamental need. We have to define the physical quality. So maybe I'll write it down here. We have to define the physical quality. So in our example, this was the distance. But there are also some physical qualities we cannot define. Let's say about intelligence. Is there any measure on intelligence or comfort?
Thank you.
The IQ test, yeah. The IQ test is a good example for measuring intelligence. But if you know the statistics, if you do a lot of intelligence tests, according to the tests, you're all the time getting more intelligent and more intelligent. So, there's obviously one thing wrong. Do we really get more intelligent if we're doing intelligence tests? Or what might be the other problem with the test?
Maybe they know the answer.
Maybe you know the answer. Yeah? So most of the time is some mathematical questions or logical questions, and you have to answer a number of questions within a certain time limit. But the more you do this, the easier it gets. So it's not that your intelligence will be improved, but simply the measure is wrong.
So there is no accurate measure for the intelligence.
Yeah. So it's not scalable. And what is the unit of intelligence? There is no unit. You have a certain number, maybe, I don't know, 150 or 90 or whatever, but this doesn't give you any further information on intelligence. These are also arbitrary numbers. You can't compare from one human to the other, but as I told you, the more tests you did, the better you get. So there is one critical decision. You can start to do many tests as possible and hope that you will get more intelligence, or you can follow your studies. So it's up to you. But the intelligent is one typical example for not having
Unit.
a unit and a well-defined physical quality. Because no one can really tell you what is intelligence. Huh? So depending on if you're asking a physicist or a psychologist, there is quite different argues about that. So there is no defined quality or a well-known definition on intelligence. Huh? And there are a number of other examples for that. But for physical qualities like the distance or the weight or light intensity or amps, current strength, there is a standard, and this is a well-defined physical quality. The second point is we will need a unit. If there is no unit to the corresponding physical quality, it's also not possible to do a measurement. Because the measurement, x, is all the time given by a numerical value, x, times our standard, or unit. And that's what we are talking today, is this standard n. So for every physical quality, we ought to have a definition and we ought to have a standard or a unit. If we fail on one of them, we cannot do any measurement. It's hard to have only one standard. But maybe you should improve your
Yeah, I will.
with some.
Yeah, after that, make my sensor first.
Yeah. So, that's what we will need, and that's what we are talking today about. This is the standard or the unit for the corresponding physical quality. As we have seen with this example, distance, there is a naturally arising standard, that's the feet, or step wide.
But we know the unit of this one.
We know the unit, they're feet.
Yeah, I'm talking. It's different between feet and meter. Meter, we don't know what is meter.
We don't know what is meter, yeah?
But we
the
know what
meter
is feet.
arises from the step length.
Mm-hmm.
So, but this is an example you see. If you're walking along some path, then depending on your physical condition, the step height will be different. The same will be if you are a small person or a tall person. So there will be substantial differences in the step length. So
You have to calibrate.
you have to calibrate, but that's the problem. How do you calibrate a human? Huh?
Calibrate with the units, with the defined unit.
Yeah. And that was the problem, that prior the French Revolution, all the units were derived from a human being. You see it especially in Vienna. If you go to the St. Stephen's Church, there is also the length of this bone here was defined as a distance of measure, but as we know, the length of this bone is also changing. So the idea of the guys from the French Revolution was to get rid of this standard system, the human standard system. They tried to get some natural measures. So, and this was the idea of the meter. And up from the French Revolution, the meter was defined as 1/40 millionth of the circumference of the Earth. you will see, this is not very practical, because on the one hand, no one could measure the circumference of the Earth. And how do you divide this by 40 million?
Why no one can get the circumference of the Earth? It's now measurable with the satellites or something.
And now it's measurable, but remember back to
Yeah.
1800, there were no satellites up there, or at least we don't know it.
And
But
also it's like
At
an
that time it was pretty complicated, but it was the first idea to get rid of step size and feeds. And this was developed, and around up to 1960 we have the so-called Urmeter, it's called. This was a rod with two marks on it, and the distance between these two marks was defined as 1 meter. So, but the problem was that there was worldwide only one rod of this, and everyone has to obey to this standard. And this is pretty much of a problem, because the standard was lying near Paris, and if you are, for example, in Vienna, then you cannot access this standard. So this was the problem of the original Urmeter standard. Yeah? So then this was overcome in around 1970, and up from then the meter was defined via the speed of light. But since the speed is the distance per second, first of all we have to define a measure for time, and this we will do first. So the SI system, it defines only 7 standards, or standard units. But as you know from physics, we got a multitude of different units, but these are the primary units. All the other units are derived from these
Primary unit.
standard units. Yeah, these are the primaries, and the secondaries are derived. So there are only 7 primaries. One of them is the second, the unit for time. So how can you define time? Any idea? How was this done?
With the sun movement.
Sun movement, but there we are really at ancient times. But it was done with the sun movement from sunrise to sunset,
Yeah.
and it was divided by 24. This was a magic numbers of
Why
the ancient.
24?
This no one can tell you, but the so-called ancient population, the Sumer, I don't know what they're called in English. So they divided 1 hour by 60 and 1 day into 24 hours. But they were not bounded to the decimal system, so they had also a different numbering system that was based on 60, not on 10. But as the human got 10 digits, then we shifted to
10.
the decimal system. Because 60 is too much.
6 units.
But they defined that the time was from sunrise to sunset. And they divided the amount of time by 24, by 60, and by 60, and then we end up with 1 second. But the problem is, now if you would like to have a standard for 1 second, you cannot wait the whole day. You divide it by 24, 60, and 60, so there must be some other measurements.
But they started with the day and the year first, right?
Yeah. And then this was important for agriculture to bring out the corn. But later on, there have to be some means to measure this 1 second. And the first ones were from the Chinese. They had some water clocks. That were some, like a pot or something like that. And there was a small leak in the pot. And then there was water dropping out of this pot. And there were a rate of 1 drop per second. But you can imagine that this will change with the pressure in the pot. So it was not very stable, but these were the first known clocks. Water clocks were based on water drops. This was improved later on.
The sand clocks.
We skipped that.
Okay.
But you can also, this we have until nowadays, the sand clocks. And the sand is going down. But then you had, this was, you have to have 2 marks, and as long as the sand takes from here to here, but for 1 second, then you can have 1 minute maybe, yeah, but 1 second is, this was easier for 1 second, because you have, it's easier. This one is pretty complicated. So sand clocks, still functional, but not for seconds, so maybe for 10 minutes or 5 minutes, you will have it. But the first viable things were the pendulum. Because here, now you have a combination of standard and physics. Because how is the period of the pendulum defined? This seems to be my number. Any idea? What is it depending on? The period?
Momentum.
There's only one parameter, the length. So, out of this you can set up a clock so that the movement of the pendulum is that from one extreme to the other is exactly 1 second. And these were the first clocks that you can carry with you, because these clocks were pretty heavy. If you got a big pot, maybe for 1 hour, and then you all the time need to refill it. But these were, they were very popular around 1600 up to 1800, because this was the age of the seafarer. Now you got the English people and the Portuguese and the Spains, they were traveling across the ocean, and they have to know the time. Why should they know the time? Why for? Why was it so important to know the time?
To navigate.
If you're on a ship. To navigate? Why?
Because they needed to know the angel of stars and sun and need to know which time it is, because then they know
Yeah.
the current position of the Earth relatively.
If you are traveling,
system.
maybe on the Earth, there is the sun, much more away here, but depending on the latitude, the angle from the surface to the sun changes. And this was the critical thing, because if you're traveling from, let's say this is Europe here, not very good, but this maybe you're traveling like Columbus did to travel to India.
America.
He didn't know that America was in between. Then there are the system of trade winds. So it depends where you are, here or here or here, the wind will blow you in a different direction. And if you are traveling around here, then the trade wind will blow in this direction. And if you are traveling more to the north, then the wind will get you back to Europe. That was, he didn't know that, So it was very lucky that we have these trade wind systems, otherwise it never would have come back. And therefore you need your latitude, the position here. Because if you're leaving that strip of trade winds in the middle and going too much to the north, then the wind will blow you back to Europe. And therefore you always have to measure the wind, the angle to the sun exactly at 12 noon. Because if you're changing that time, then as you know the angle, the sun angle is different, and so you will not get back. So this was the first time humans really built clocks.
And what was the range of this rotation?
Of the pendulum.
Yes.
So it's maybe 10 to 15 degrees.
So
What do you mean the precision?
I mean, they set this, for example, angle for.
No, they set the length,
Okay.
and the length will give you exactly a period of 1 second.
Okay.
If you change the length,
So they should know from where they have to release that pendulum to go and back.
no, they were driven by a spring. As you know, these old clocks, maybe your grandma got one, and they were driven by a spring, and this was going on all the time, and the elongation was pretty constant, because the harder you hit the pendulum, the period is the same. It moves just faster. So it doesn't make any change if you have that angle or that angle of pendulum movement. The period is just the same, but it's faster. If it's going from here to here, then it has to move faster. But the frequency, the swings per second will stay the same. So it's not depending on the elongation. That's the idea of the pendulum, and also that's the idea of every musical instrument. For example, if you're thinking about a guitar, no matter how hard you
play.
hit the string, it's the same frequency. And it's the same here. Because if the frequency of the string would change with the amount of elongation, then every musical instrument will maybe not blow, but it will sound completely different like we're used to it. So you cannot play a piano or something like that. Yeah? No matter how hard you hit the key, it's the same frequency. It's louder, but it's the same frequency. Yeah? And that's the same with the pendulum here. No matter how hard you hit it, it will go with the same frequency, the resonant frequency. It's also a resonant circuit, not an electronic one, but a mechanical one. Yeah? You can make this experiment. It's quite easy. Take a mass, a string, and let it travel to a bigger elongation, and just check all the time when it hits the middle position.
In the middle position is 1 second.
It depends on the length here. It's a function of the root of the length. No? But it's only depending on the length, not how hard you hit it or whatever you do.
One is 1 second.
Yeah. For this clock, then one turn was 1 second. Yeah? And the same we are using nowadays, not a mechanical assembly, but it's more or less comparable. But you can imagine if you took such a clock on a ship, it was not very precise during rough weather.
Yeah.
Because the ship was moving, also the clock is moving. So the precision was not very brilliant, but you had around 1 second per half a day. But it's better than nothing. Today our clocks are
Digital.
much more precise. If you use just a low-cost crystal clock, then you have around 1 second within 1 or 2 days. But to get to the standard of the second, we have the same principle, but we are scaling the size down. So what we're using today is more or less also a pendulum clock, but the size of the pendulum is very small. We are using atoms as a pendulum. So what we are doing is we are taking a cavity. This is just a box. There is nothing in it. So we pump out all the air, so there's nothing in there. And then we put in cesium-133. Why do we take cesium-133? This is one of there are not so many stable isotopes, but this is one of the stables we got. There is also cesium-134 and 136, but they will fade over time. So what will remain is only cesium-133. And this atom will act as a pendulum clock. But you can imagine that the movement of the pendulum is not once a second. It's a little bit more. So it's 9,192,000,000, and I think some 631 and 77 movements per second.
A little bit more, yeah.
A little bit more. But it's also a little bit smaller in here. But the question is, how can we measure the pendulum movement of the atoms? That's the problem. So what we're doing is we're putting in here some antenna as a transmitter, and we are transmitting a frequency to that cavity. And what we are doing is we are measuring the energy that we can transmit to these cesium atoms. And if we alter the frequency, so if we alter the frequency and monitoring the energy over this frequency change, then we see that at a certain frequency we got a very sharp peak. And this is the resonant frequency of cesium-133. And the fine thing with this stable isotope is that we got a very sharp peak. So it's a very small. So if we have only a small variation from our resonant frequency, the energy will drop, and then we know that we are away from our pendulum frequency of the cesium. So that's the idea. And if we are using some other materials, so every atom has its resonant frequency. So because every atom is like a pendulum, maybe we are using some other material, then maybe our resonance curve will look like that. And here we cannot detect the peak, because this is a very shallow slope, and we cannot detect the peak. But here it's a very sharp peak, and that's the resonant frequency of cesium-133.
So we cannot detect the peak accurately here.
Exactly. So the sharper the peak, the more precise we can detect the resonant frequency of the element.
So the
Do we know all these numbers for these cells? And do you make these
Some of them.
calculations?
Some of them. Yeah.
So you got the video, you have
I don't upload it.
You don't have to know the exact numbers, but you have to have the idea where we are. Is there 9 Hertz or 9 periods per second, or is there a million or a billion? So this would be. But you don't know, you have the exact numbers. But you have to know that this cesium,
133.
yeah, and maybe not nitrogen or.
Uh-huh.
Because the same thing will work with nitrogen, yeah?
Yeah, but
Or
with different.
oxygen.
But with we cannot detect the peak accurately.
Yeah, because then the peak is much more shallower and you cannot. But there is one other measurement based on oxygen in prehistoric measurements. Huh? Do you know that?
No.
Or carbon. It's carbon 14. Carbon 14 is not stable, so it fades over time. And carbon 14 is only aggregated into living objects like a tree or a plant. So if a plant is an object or not, we don't discuss about that. But if the plant is dying, then the aggregation of carbon 14 is stopped, and this will fade over time. And then you can measure the coefficient between carbon 12 and carbon 14, and then you can estimate the age
Age of the tree.
of that tree. Or
Any
some
object.
Everything.
bones,
Also bones.
But just have to be living thing.
the living thing, yeah.
So how they estimate how they know the age of some objects, for example,
This is
papers.
an estimation.
And they have
Uh-huh.
references.
Yeah,
For example, they found old trees
yeah. If you have the coal
down there.
buried in this same layer, then you can link, okay, all the things in that layer are from the same period of time. And if there are some bones in there, then you can detect it.
Estimate.
But most of the time this is an estimation, and some say this is wrong. So maybe the dinosaurs are not living 100 million years ago, but only 50 million years ago. But
Oh.
don't mess about that. But what we can do with carbon 14, you can have the exact numbers, but this is rather in the area of 100,000 years, so maybe not 100 million years. But we don't care about that. What we're caring about is our cesium-133. And the cesium is one of the few elements with only one stable isotope. Therefore, we get cesium into this atomic clock. And this atomic clock, you can have a precision of 10 to the minus 14th. That means this clock has it waits by 1 second if you wait for 10 to raise to the power of 14 seconds. And this is a pretty long time. Huh? So the newest ones, they are working with lasers. They are even more precise. They come up to minus 16 as a precision. So whatever you are measuring, the time is the best quantified quality in physics. There is nothing you can measure with that precision besides time. So the seconds is the best defined we got. So this,
That's the atomic clock.
based on the atomic clock. So with every GPS satellite, you've got one atomic clock on board, because otherwise it wouldn't work. You need the precision of this atomic clock because of the runtime of the signals.
Excuse me, when we get the resonance frequency of silicium 133. Okay, after that, what calculation we do for getting the exact?
The rest is electronics. So it's a frequency of 9 gigahertz, and you are counting. So out from here, you have the frequency generator. It's a tunable frequency generator. Via the energy, you tune it to exactly that number. And after that, you have a counter. And this counter counts up to this number. And after that, it gives you a signal, and that's exactly 1 second. Yeah.
And what does this counter exactly count?
This frequency.
What does the cesium atom do?
The cesium atom is only the standard. So this is a tunable frequency generator.
Yes.
You can tune maybe from 9 gigahertz up to 10 gigahertz.
Okay.
And during this tuning process, you are measuring the energy you can get into this cavity. And if you are reaching the resonance frequency, then you see that there is the maximum of energy you can get into this cavity.
Okay.
And here you will stick your frequency counter. So the frequency generator just is varying a little bit around that peak.
Okay.
So that's locked to this frequency. So it's more or less locked to the resonance frequency of cesium. Yeah? So this frequency generator is locked and it runs with a frequency of 9,192,000,000 hertz. And this you will send to a counter. And if the counter exceeds that number, then it rolls over again to 0, and that's 1 second. So out of this counter, it counts up from 1, 2, 3 until that number. And here it rolls over and starts again. And this signal has exactly a period of 1 second.
The counter counts the peaks.
No, it counts not the peaks, it counts that frequency.
Every
Every
nine.
Frequency?
Every amplitude.
Oh. You don't know what's frequency?
No.
Okay, then. You have to tell me that.
No,
So-
we know what is frequency. I know what is frequency.
Every wave. So it counts every wave of the signal.
Yeah. This is pretty hard then to explain, but so what's frequency? You can remember, what do you know? The maybe a sinusoidal
The waves.
waves. Let's stick to the pendulum, yeah? The pendulum swings. And maybe you put here a pen on the pendulum, and this pen draws on a paper strip that is dragged into this direction. And if you follow that movement of the pendulum, that will give you this sinusoidal graph here. And now that's the problem with standards. Now we have to know what is 1 second. But if we start here and we wait for 1 second, let's say this is 1 second. So we move the strip with a certain speed, 1 second. Then we come up here. And then we are counting the peaks. It's 1, 2, 3, 4, 4.5, 4.6. Let's say it's 4.6. Here we will get 5. And now the number of full excursions per second
4.6.
is this what we call frequency. Yeah? So the frequency of this movement is 4.6 hertz. And hertz is 1 full excursion per second. So maybe if you have the tire on your car, you mark 1 point, and this is rotating.
In 1 second.
And then you count how often this point will pass you within 1 second. Then you know
The frequency of the
the
time.
number of rotations per second is the frequency.
The movement of pendulum is infinite. I mean, there is no loss because of the weight.
Here it's no loss, because there is vacuum. In practice it's not. This movement will stop. So if you set it to movement, then the elongation will go slower and slower. and that sometimes the pendulum is still, because of the air resistance. Because the pendulum is moving through air, it has to shift away the air molecules, and this will reduce the movement of the pendulum. But this is what we call frequency. It's the number of cycles per second. So these small atoms do 9 billion cycles a second. It's a pretty, but it's 9 gigahertz. On a technical scale, it's a pretty high frequency, but it's manageable.
And what information are we getting from the energy?
From the energy, we got the information about the resonant frequency of the cesium atom. Because this generator, you can tune it to every frequency.
But the cesium wouldn't react on another frequency.
Exactly. So if we are here, the cesium would not react. We cannot get the cesium to absorb our energy. So this is like an antenna, like the antenna on a mobile phone, transmitter. It transmits energy into this cavity. And if it's the wrong frequency, the energy gets reflected and it comes back to the antenna. The antenna receives the energy, and so we don't need any energy here.
So other frequencies would be just absorbed by the atom and not...
So only this resonant frequency will be absorbed by the atom, and therefore that's the mark for our resonant frequency of the cesium.
But isn't it a hand-egg problem? Because when I need the frequency generator, I also need a...
Calibrated, you need a scale. So that's all of the units. It's a hand-egg problem, because 1 second is pretty arbitrary, but on a historical scale it was developed out of these pendulum clocks, and now we got the same on a very small physical scale, but this number is not given by physics. This number is given by history, because we wait such a long time so that this clock is compatible with the old pendulum clocks for 1 second. Yeah?
That's what I was gonna say.
It's not
Because
given
we
by
need to define what is hertz, we need seconds also.
Exactly, yeah.
It's a loop.
So maybe if history would have gone different, we might have 10
Yeah.
billion hertz, if the second is a little bit longer. But we ended up with that number. But this is with every standard. It's the same with the meter. To define the meter, you have to have the meter.
Yeah.
Yeah. And to define the seconds, you
Have to have second.
have seconds to define the frequency, this frequency. Yeah? So it's all the time the same. So as I told you, there is no measure in physics that will give you any information about the length of 1 second. Yeah? That's an arbitrary number. But now we got it. It's 9 billion cycles of these cesium atoms. And this arrangement we only need to find the absorption frequency of cesium. So is everyone clear about that?
Yeah. That's the clock they use in the satellite.
That's the clock they're using in the satellites. And the advantage of the second is that every lab can have its own atomic clock. So it's not the same price like your pocket watch, but it's not that expensive. So that's a very good standard for the second, because it's movable, it's available all around the world, and it's bound to a physical entity, the cesium. So it's based on physical principle that we do not have with the mass. So the first was the second. The meter we had before, so we can focus again on the meter. So if there is another expression you are not familiar with that, then just ask, because I cannot know what kind of expressions you know and what not. So the seconds we had is the length, or the meter. So the meter, as I told you, there was originally one metal rod with 2 marks on it, and this was given as the meter. But nowadays it's defined via the velocity of light, because Einstein defined the velocity of light as a constant number. How fast is the light in vacuum?
Yeah.
There's another number for you.
300,000.
And this was defined. So it's not, nowadays it's not useful to measure the speed of light, because it's defined to that number. There's no more discussion about the speed of light. It's defined to that number. So if you look in old physics book, there you got the number 456.2 meters per second. That dates back to that time when the meter was defined by this metal rod. But nowadays this definition is not more valid, and